And we say that the MOS transistor, the basic structure is a capacitor. This capacitor has two conductive plates. One is poly, and which is the gate, and another plate is the semiconductor, which is lightly doped by p-type silicon. And actually, we form a capacitor as a structure. So by applying a vertical electric field, we can generate some carriers underneath the gate, to be here. So by applying the vertical electric field, actually we can have some carriers. In this case, electrons. And by applying another horizontal electric field, we are able to move these free electrons. So this is basically the idea of a MOSFET. So we have two electric fields. One is vertical, which generates the electrons which are in the channel. And the other one is the horizontal electric field, which will force these generated electrons to flow in the channel. So basically, there are two terminals beside the gate. One is source and another one is the GEN. And how to define source and GEN depending on the bias voltage. Okay, so actually the carrier will flow from the source to the GEN. So in the case we just talked about, if we bias the GEN with a higher voltage, bias the source with a lower voltage, then we'll generate an electric field. The direction is from GEN to the source. And if the carriers are electrons, the electrons will go from source to GEN, okay, resulting in a current actually from GEN to the source. So basically, if we swatch the bias voltage between GEN and source, then the direction of the current flow will be the opposite. Okay, so you have to pay attention how you bias the transistor. Okay, so we say that in order to form a channel which contains electrons which are able to flow, we have to bias the gate voltage to exceed some threshold voltage. This is called threshold voltage. If the gate voltage is smaller than the threshold voltage, actually there will be no channel formed and there will be no current. Only when the gate voltage is larger than the threshold voltage, then we can form a channel. And this channel, there will be some free electrons in the channel. So these free electrons can be forced to move by electric field between the GEN and the source. Okay, so the first idea is that you have to bias the gate larger than the threshold voltage in order to form a channel for current flow. And so we see that there are two terminals that we can use to bias this transistor. One is the gate terminal and another one is the GEN terminal. If we fix the GEN terminal so that we can have a constant electric field, then we increase gate voltage from 0. So before the gate voltage exceeds the threshold voltage, there's no current, but after the gate voltage is larger than the threshold voltage, actually we will have current, and this current will increase with as we increase the gate voltage. But it is not linear. Actually, later today we are going to see this is a square law relationship. And if we fix the gate voltage and we change the GEN voltage, basically if the GEN voltage is not very large, what we are going to see is a linear relationship between the GEN voltage and the GEN current. So it kind of looks like a resistor. Okay? And yesterday we also talked about some dependence on the parameters. The current is inversely proportional to channel length. The current is inversely proportional to oxide thickness. and the current is linearly proportional to the channel width. Okay, so these are just some flashback from yesterday, and we talk about the channel potential variation because how much charge can be formed in the channel depending on the voltage across the channel. Okay, so the voltage across the channel is the largest at the source side because this is gate voltage and the source voltage right now is tied to ground. It doesn't need to be tied to ground, but we will tie the source voltage to ground at this point for simplicity. And the voltage across the channel, the gate oxide, is actually Vg minus Vd. So actually the voltage right here is smaller than here, okay? And this is the reason at this place, actually the charge induced in the channel is larger than the charge right here, okay? So actually the charge, the amount of charge along the channel is not a constant. Actually, you will decrease from the source side to the drain side. Okay, and the channel potential, we call it V of X, okay? Starting from 0, which is the source side, and ending at drain, which is Vd. And it is not a linearly variance. Actually, it has some function, right, like this. Okay, we're going to see this later today. So the formation of the channel will not be just a homogeneous channel. Actually, it will have this kind of shape. Okay, so if the Vd is not large enough, Vg minus Vd still larger than the threshold voltage. At the drain side, we still can see the channel. Okay. But if we keep increase Vd, we'll reach a point that Vg minus Vd is exactly equal to the threshold voltage, which means that there will be no charge generated right here. Okay? So we say that the channel is pinch off. Pinch off. And if we keep increasing Vd, what is going to happen is that its channel, the length of the channel will actually shrink, will actually be shrink to here, okay? So the channel length was L, it may become L1. So what will the operation of the transistor happen after Vd is larger than this pinch-off point? Actually, we talked about this yesterday. The current will still flow because there will be a reverse bias electric field right here. So whatever electron goes to here will be swapped into the drain. Okay, so it will still conduct current. Let's assume that L1 is very small, very close to L, which means that that's our assumption is this delta L, which is we can call L minus L1, is very small. Then after the pinch off, the current will stay constant. That's why we say that the transistor will be a voltage control current source. Okay, this is where we stopped yesterday. So let's continue from here. So we see that the transistor can function as a voltage control current source. How much is the current? Okay, so today we are going to deduct some formula. So to deduct the formula, actually we can look at this structure. So first we define a quantity called channel charge density. Okay, what is channel charge density? The channel charge, which is the charge in the channel per unit length. Okay, if we go from here, the source side, to the drain side, if we go for 1 unit length, how much is the charge underneath this length, okay? So this is what we say channel charge density. It's defined as the channel charge per unit length, okay? How much is it? Actually, we have to see two things. The first thing is that the charge is equal to the capacitance times the voltage, right? The voltage is the voltage across the capacitance. The capacitance is C is equal to W, which is the channel width, times C oxide. What is C oxide? C oxide is the gate capacitance per unit area, okay? This is the oxide capacitance. So this is the oxide, this is the gate, this is the semiconductor. So C oxide is the oxide capacitance per unit area. When we times C oxide by W, we calculate this capacitance per unit length, right? Because area is W times L, okay? So for unit length, the capacitance is C oxide times W. So actually Q is equal to W times C oxide times V. What is V? At the source side, V is Vg minus Vs, right? If we tie Vs to ground, at the source side, actually V equals Vgs minus Vth. Okay? So Q is equal to C times V. C is W times C oxide. V is equal to Vgs minus Vth. So we can write down this formula. Okay, so it looks a little complicated, but actually it is Q equals C times V. All right? So this is the channel charge density. However, we just mentioned that the charge density is different at different location of the channel, right? Because at different location, actually the voltage across the capacitor is different, okay? So we need to keep this in mind. Channel voltage is not a constant. This channel potential is not a constant. It's V of X, right? We just mentioned. So because the channel voltage is V of X, actually the voltage across this capacitance is not VGS along the channel. Instead, it's VGS minus Vx at any given point. Okay? If we look at right here, then this is V of X. Then the voltage across at this place is VGS minus V of X. Okay, so Q is not a constant along the channel. Instead, actually, Q is a function of X when we look at different position of the channel. So if we want to calculate the current, let's see, how do we calculate it? We just see if, what should I say? Okay, so basically, we define the channel charge density, right? The channel charge density is the charge for unit length. And what is current? What is current? Current is divided by the charge divided by time, right? The unit is coulomb per second, okay? So in the unit time, how much charge can flow? This is the definition of a current, okay? For a unit time, the unit could be a second. How much charge how much Coulomb can flow within a unit time. Okay, so this is defined by this is the definition of current, and actually the unit of current is amp. How many amps? Okay, so basically, if you remember, the definition of current is in a unit time how much charge can flow, right? We just define a channel charge density, which is the charge per unit length. And in a unit time, how much length can we have? Okay, so if the velocity of the carrier is v, velocity. If the velocity of a carrier, which is the electron at this case, is v, the unit of velocity is m divided by second, right? In the unit time, how far the distance this carrier can go. So this is the velocity. The velocity times 1 unit time is how far the carrier can go in 1 second. Okay? So this is v, the unit is n. Okay? This means that in 1 unit time, and the unit time is second, in 1 unit time, how far can the carrier go? This is v, okay? So this is the length of the charge that need to be covered in 1 unit time. So we know that the channel charge density is the charge per unit length. Therefore, in 1 second, actually, the charge that is involved should be the channel charge density times the length. The length is actually v. Okay? So how much charge is the channel charge density times v is the total Q. Okay? So I is Q times v. Right here. We can also look at the unit. See, I is Coulomb second, right? Equal to Q. What is Q? Q is the Coulomb per unit length, right? Remember what is Q? Q is defined as the unit, the charge, channel charge density, right? So Q is the channel charge per unit length. So it's Coulomb divided by meter, okay? And then times V. What is V? V is meter by second, okay? So you can see Q times V equal to I. The unit is Coulomb divided by second, okay? So if you look at how to match the unit, you can understand as well. So Q here is what we define as the channel charge density, which is the charge per unit length, okay? And I is the current actually can flow in the semiconductor. It's the total charge that passes through the cross-section of the bar in 1 second, okay? So the current is in 1 second, in 1 unit time, how much charge can flow. And V is actually the speed, not the speed, the velocity of the carrier. In this case, is an electrons. Okay, so what is Q? Oh, okay, anyway, Q we know. What is V? V is equal to mobility times the electric field. Okay, this is the definition of the carriers. I think you learned this in the microelectronics class. Okay, V is equal to mobility times the electric field. And the electric field is actually the derivation of the potential difference. Okay, so your electric field is the derivative, not the derivation, derivative of the potential difference. Okay, so you should get this from general physics. So if we substitute that into here, we see that the velocity is mobility times dv over dx. V is the potential difference, the potential field, okay? So this is the derivative of the potential. So I, which is the ID, is Q times V. What is Q? Q is W C oxide times this, okay? What is V? V is mobility times the derivative of the potential. If I move dx to here, actually we can do the integral of both sides, okay? One side is to see from the source side to the drain side, which is x equal to 0, this is the source side, to x equal to L, this is the drain side. So we integrate all the charges together to get a total current from the source side to the drain side. This needs to be an integral because the carrier, the channel, is not the amount of charges along the channel are not the same. Okay, so we need an integral to do this, and corresponding to x equal to 0, which is the source side, actually we should see this is from Vx of 0 to Vx equals to Vds. When Vx is equal to 0, this is the source side, okay? When Vx is equal to Vds, this corresponds to the drain side, okay? And then is the integral. So if we integrate this, then we can have this formula at the end. ID is the drain current, is equal to 1 over 2 times the mobility times the oxide times W over L times 2 VGS minus VTH times VDS minus VTS squared. Okay. So this is the governing equation of the MOSFET transistor. Actually, it works in all the regions for the MOSFET transistor. Okay? So this is how we get this formula. This formula is based on how based on the physics, the mechanism, how we generate the charge underneath the gate in the channel, and how we move this charge by electric field. Okay, so all this formula actually has a physical meaning. Okay, so now we have this formula. Let's look at it a little closely. Okay, the first thing is that, okay, this part is very important. 1 over 2 times mobility times C oxide times W over L. This is a very important quantity of the MOSFET. Actually, what is mobility? Mobility is the mobile ability, which is a property of your carrier. Okay, you only have two kinds of carrier. One is electron, and the other one is electric holes. Okay, the mobility of electrons is about like 3 to 4 times the mobility of the electric holes, which means that it's easier to move electrons. Okay. So this is a constant. You have nothing to do with this. Okay, you cannot control this because this is a constant. Another thing is called C oxide. Remember what is C oxide? C oxide is the gate capacitance per unit area. Okay? So this is the C oxide. This C oxide is the C oxide is Armstrong oxide divided by T oxide. Okay? Armstrong oxide is a constant. It only depends on the material. Okay? For the gate oxide, it's just depending on the property of the silicon dioxide. So you have nothing to do with this. And the thick oxide, no, not thick oxide, the oxide thickness, T oxide, is another parameter that you have no control. Okay? The foundry actually decide how thin, how thick this parameter is. Okay, so this is C oxide. The thing you will have control is W and L. Okay, one is channel width and another one is channel length. And just like what we mentioned yesterday, you can see the current is proportional to W, the current is inversely proportional to L, and the current will be inversely proportional to T oxide. Okay, so the formula said it well. And actually, because W over L is what we can control, we give it a name called aspect ratio. Okay? So W over L is what we call aspect ratio. This is what designer can have control. We can decide how wide the transistor is. We can decide how long the transistor is. Okay? So these are the two parameters that we can have some control. And if you look at this formula, you'll see for constant VGS, if we fix VGS and we swing VDS, IDS will vary parabolically with VDS. Okay? So basically, if we fix VGS, you'll see as we increase VDS, actually ID is going to increase. But gradually, the drain current will reach a maximum right here. Okay? And the maximum happens when VDS equal to VGS minus VDH. Okay? And if we keep increase VDS, actually, you like this, or you will be like this. But actually, it will not. That's why here it has some dot line right here. Okay? So one thing you know is that if you increase VD, you are going to see an increase of drain current until the drain current reach a maximum. Okay? And when it will reach the maximum, depending on VGS. If we have different VGS, actually, the drain current, the drain voltage will reach maximum at different voltage. So you see, this is VGS for VGS1. The drain voltage that will reach a maximum is VGS1 minus VTH. If we set the VGS to VGS2, and you can see actually the maximum current happens when VDS equal to VGS2 minus VTH2. VTH, okay. So basically the maximum of each curve are different. Okay, it actually depends on the value of VGS. If we increase the VGS, actually the maximum happens at larger VDS. And if we connect these dots together, it's another parabola. Okay, this is another parabola. Okay, so we just mentioned that the maximum drain current happens at when VGS equal to VDS equal to VGS minus VTH. So if we substitute this, if we substitute VDS as VGS minus VTH into this formula will result in the maximum current equal to this. The maximum current when VDS equal to VGS minus VTH is 1/2 mobility C oxide W/L VGS minus VTH square. Okay? And this is the formula you should memorize. You should memorize. 你们要记得这个公式。如果不记得这个公式的话，将来去这个业界 review 的时候，记得这个类比是别人修别人的，不是修我的哈。这个公式是一定要记得的哈。这个学 MOSFET 不可以不记得这个公式哈。我可以讲几个老师的名字给你们选，这样子。好 ，OK， 好 ，So you have to memorize this, okay? So ID is equal to 1/2 my mobility C oxide W/L VGS minus VTH square, okay? So here you can see actually the gen current is squarely depending on VGS, right? Because there's a VGS square. Okay, so it's a square law. It's a square relationship between the gate voltage and the gen current. Okay? So the first thing we know here, the gen current depending on the square of the gate voltage. So let's look into this in a little more detail. So this is VDS, right? The x-axis is VDS. What happens when VDS is very small? It looks very linear, right? And if you remember, we mentioned earlier today and also yesterday, VDS and gen current is actually linearly dependent. It behaves like a resistor. So what happens when VDS is very small? Okay, so this is the governing equation. If VDS is really small, actually we can neglect this part because a very small quantity square is even smaller. Okay, so if VDS is really small, actually we can neglect this part. Then the gen current will be approximated to this. Okay, and 2 times 1/2 is 1. So the gen current will be mobility times C oxide W/L times steps, VGS minus VTH times VDS. Okay, so when VDS is very small, actually you see the gen current is linearly depending on VDS. Okay, so this is what happened. This is what we saw before. It looked very linear, right? It looked very linear. Actually, VDS and ID is linearly dependent when VDS is very small. Okay, and you have to remember, it only happens when VDS is very small. Okay, so it looked like resistance and resistance or the unresistance can be written as this. Okay, the resistance is VDS over ID, right? So it's this and inverse. Okay, and as you can see, actually this would function as a resistor, and the resistance is controllable with a gate voltage. Okay, so it's a voltage control resistance. If you increase the gate voltage, actually you will decrease the resistance. Okay, anyhow, you can control the resistance by control the gate voltage. This is when VDS is very small. Remember that. When VDS is very small, the MOSFET can behave as a resistor, which resistance can be controlled by the gate voltage. All right. So then we see the transistor, actually, if we plot this plot, the x-axis is the VDS, the y-axis is the drain current. When we increase the drain voltage, the drain current will increase, and then it will reach a maximum. And after this maximum, it will become a constant current source. Why is that? If you still remember, what is this point? This point is when VDS is equal to VGS minus VTH, right? So what is this point? This point is what we actually saw in our previous slide, is this one, okay? When VDS, VG minus VD equal to VTH, okay? Which means that VD is equal to VG minus VTH at this point. And this point is called pinch off, okay? And we assume that after pinch off, if we keep increasing the drain voltage, the channel actually will shrink toward the source side. But remember our assumption, we said that we assume L1 is very close to L. So after pinch off, if we keep increasing the drain voltage, the channel will stay more or less like this, and the current will stay constant. That's why it's a constant current source. And don't worry, later we will talk about the effect of channel shrinking. But at this point, we know that after this point, when VDS equal to VGS minus VTH, then we'll get into the pinch off point. And after pinch off, the transistor will just, at this point, flow a constant current. So that's why we call this region trial region, and we call this region saturation region. Okay, that's the definition of the name is very clear. What is trial region? Trial region means that we have three terminals, and the voltage of the three terminals actually will control the drain current. Okay, trial is 3, right? Triangle. So trial means 3. Okay, we have 3 terminals. One is gate, one is source, and the other one is drain. Okay, so in this region, actually, the drain current is controlled by 3 terminals. That's why it's called trial region. Okay, the drain current is controlled by gate, source, and drain. So it's called trial region. And until this point, actually, if you even if you keep increasing the drain voltage, the current is saturated. That's why this place is called saturation region. Okay? So now you understand the definition and the naming of these 2 regions. One is trial region, another one is saturation region. And in the saturation region, you see the transistor actually behaves like a constant current source, right? Because if you vary the drain voltage, actually the current will stay the same. So actually the transistor is behaving like a constant current source in the saturation region. And this is very, very important. Unless we mention that the transistor is doing something else, along almost all the circuits that we will cover in this semester, we need the transistor to function, to operate in the saturation region for all the transistors to work. Okay? So the transistor in saturation region behaving like a constant current source is very, very important. Remember to bias your transistor in saturation region. Okay, and in the trial region, we can kind of classify the child region into two regions, or maybe we can get into a little more detail. If VDS is really small, then VDS and ID, the drain current and the drain voltage, drain to source voltage is linearly dependent. It behaves like a resistor. This region, we call it deep child region. Okay? So in the deep child region, the transistor behaves like a resistor. And if we leave the deep child region and enter into child region, actually we saw that governing equation. And after the transistor, the channel is pinch off, it enters into the saturation region. And because we assume that after pinch off, if we keep increasing the drain voltage, basically we'll see this. If we keep increasing the drain voltage, the integral of this will change a little. So from 0 to L, it will change to 0 to L1. Okay, this is still 0 to this. Anyway, so the result of the integral will be 1 over 2 mobility times C oxide W over L1. The only difference is L becomes L1, VGS minus VDS squared. So if we just assume that L is very close to L1, L1 is very close to L, then actually the drain current after pinch off will more or less the same as the current at the pinch off. Okay, so it will be a constant current. Okay, and this is what we are going to use, transistor in saturation region. And here, let me say a little more, because people used to get confused of two things. Actually, for transistor, for a MOSFET, there are two graphs which are important. One is called VGS and ID. Okay? The other one is VDS and ID. Actually, these are two different figures. What is the dependence of VGS and ID? Remember, when we increase the voltage of VGS from 0, actually there's no current. It's until you reach a threshold voltage, right? It's until you reach a threshold voltage, and then you see this. This is the dependence of VGS and ID. Okay? If we want to say this will be the off region, this will be the on region. If your VGS is smaller than threshold voltage, the transistor is off. If your VGS is larger than threshold voltage, the transistor is on. And assume, okay, assuming that the transistor in saturation region, then this dependence will be ID equal to 1 over 2 mobility C oxide W over L VGS minus VGH square, right? So if you say this, actually you assume something. You assume that the drain voltage at this time actually is large enough so the transistor in saturation region. Okay, but anyway, what my point is, if you talk about the dependence between VGS and ID, actually there are two regions. One is called off region and another one is on region. If you are in the off region, it doesn't matter what is the voltage on the drain, because there are no charge in the channel, right? If you don't generate any charge in the channel, nothing will flow. There will be no current. Okay? And another one is the VDS and the ID. So we just saw that if we increase VDS from 0, it's linearly dependent, and then it becomes parabola, and then it will reach as a constant. Okay? And actually, this is VGS minus VTH. Okay? So this part is called trial region. This part is called saturation region. So both plot has two regions, but the definition and the physics behind them are totally different. Okay? So for the VGS, actually you want to generate the carriers. You want to generate free electrons underneath the gate to flow. Okay? So you need to exceed some threshold voltage. So the two regions are off region and on region. And if you do have some carriers to flow, then you want to increase the electric field. So you increase the jam voltage. Okay? When you increase the jam voltage, actually the transistor will first enter into trial region, and after the transistor is pinch off, it will reach the saturation region. Okay? So this figure is actually mentioning the effect of the vertical electric field. Remember the vertical electric field? The vertical electric field is used on the MOS device to generate the charge in the channel. And this figure is for the horizontal field. Okay, the horizontal field is the electric field generated between the drain and the source to force the carriers, okay, to flow in the channel. Okay, so these two figures are very different, and the meaning of them are very different as well. Okay. So one more thing before we dismiss is that, remember, we made one assumption. We made one assumption that L1 is very close to L, right? But of course, it may not be the case. It may be a little different. Okay. I talked about this already. Okay. So it may be a little different. Okay. So we made the integral, if you remember, the actual current after the pinch off is actually ID equal to 1/2 mobility times C oxide times W over L1. Okay, L1 is actually smaller than L, right? Because actually the channel shrink a little bit. So actually this will not be the same as this one. In fact, there could be some modification of the equation. We usually use this. This is the place for pinch off, the maximum current, and this will be some modification term. 1 plus lambda VDS. Okay, lambda is a coefficient. It's called channel length modulation coefficient, and VDS is the drain to source voltage. So basically, it would be this current, but plus some modification. Okay, so this is just like a linearly depending function. So the slope is lambda. If we increase some VDS times lambda, is the amount to be modified. Okay, so this is called channel length modulation coefficient, and this effect is called channel length modulation. I think the name is very straightforward because the effect is because the channel length is not a constant, it modulated. Okay, the channel length actually shrink to here. And actually this lambda, you have some control. Why? Because, let's see, if we have a shorter channel comparing to if we have a longer channel, if we shrink the channel a little bit, a shrink of channel for a shorter channel, actually you will see a big effect, right? But if your channel is very long and you just reduce a little bit, it doesn't feel like too much, okay? So actually lambda is inversely proportional to the channel length. If you don't want the channel length modulation to be too serious, you can draw the channel length to be a long channel, okay? If you have a longer channel, you have a smaller lambda, then this term will not be that obvious, okay? So this is the channel length modulation. I think the time is up, so we'll stop here. 我们今天就到这边啊，下礼拜三放假啊，没事不要来。好，那就这样。那个昨天上课讲的时候有讲一个。